In this video here, we're going to take a look at linear transformations in 3 dimensions. So up to now then, within this chapter here on linear transformations, we have only considered linear transformations in 2 dimensions. And you might have guessed it then, for this video here, we want to consider linear transformations in 3 dimensions. So how do we define then linear transformations in 3 dimensions? Well, similar to what we saw then for linear transformations in 2 dimensions, any linear transformation in 3 dimensions can be defined by the effect it has on the unit vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 then. So the transformation represented by this matrix M here, so that's this 3 by 3 matrix, so we have A, B, C, D, E, F, and then G, H, I. This will map the following here. So 1, 0, 0 will map to A, D, G. 0, 1, 0 will map to B, E, H. And then finally here, 0, 0, 1 will map to C, F, I. So that's a very quick introduction there to how we define a linear transformation in 3 dimensions. Now we also need to be aware of some standard results here then for linear transformations in 3 dimensions. So let's take a quick look at those. So you also need to be able to carry out transformations in 3 dimensions that are reflections in the planes x equals 0, y equals 0, and then finally z equals 0 here. So for a reflection in the plane x equals 0, this is represented by the following matrix here. So what do we have then? I've got -1, 0, 0, 0, 1, 0, and then finally here 0, 0, 1. Then for a reflection in the plane y equals 0, this is represented by the following matrix here. So again, what do we have? I've got 1, 0, 0, 0, -1, 0, and then finally 0, 0, 1 here. And then for the final reflection here, we have a reflection in the plane z equals 0, and this is represented here by the following matrix. So again, what do we have here? Well, I've got 1, 0, 0, 0, 1, 0, and then finally 0, 0, -1 here. So just to ensure that you familiarize yourself with these results, these 3 results here are not given in the form of the book. So it's up to you to memorize these results. Okay. So there we have it. So that gives us everything that we need here then for the reflections in the planes x equals 0, y equals 0, and z equals 0. So to wrap up our introduction here to linear transformations in 3 dimensions, you also need to be able to carry out rotations about one of the coordinate axes in 3 dimensions. So for the first rotation here then, we have a rotation of angle theta about the x-axis here, and this is represented by the following matrix here. So what do we have then? I've got 1, 0, 0, 0 cos theta minus sine theta, and then finally here 0 sine theta cos theta. I just noticed here for this rotation matrix then, my first unit vector here, which would be 1, 0, 0, this is unaffected here. This doesn't change, right? And the reason for that is because we're rotating about the x-axis here. Okay. Now for the second rotation here then, again we have a rotation and again of angle theta here about the y-axis, and this is represented then by the following matrix here. So what do we have then? I've got cos theta, 0, sine theta, 0, 1, 0, and then finally here minus sine theta, 0, and cos theta. And again, just notice here then, this would be our second unit vector here of 0, 1, 0. And again, this is unaffected here. It doesn't change, right? And the reason for that is because we're rotating about the y-axis now. And then finally here, for the very last rotation, then we again have a rotation of angle theta about the z-axis this time. And this is represented by the following matrix here. So what do we have then to finish with? We've got cos theta minus sine theta and 0, sine theta, cos theta, and 0. And then finally here, 0, 0, 1. And again, just notice now the very last unit vector here of 0, 0, 1 is unaffected. This doesn't change. And again, the reason for that is because we're now rotating about the z-axis here. Okay. And again, just ensure that you familiarize yourself with these 3 results here. So just as we saw for the previous page then, and the previous 3 results, these 3 results here, these 3 rotation matrices are not given in the form in the book. So it's up to you. You either learn these 3 results here and memorize these 3 results, or you need to learn how to derive these 3 results here. So what I will do then is do a separate video here showing the derivation of these 3 rotation matrices. Okay. But there we have it. So that gives us everything that we need here then for our introduction to linear transformations in 3 dimensions. Let's take a look then at one practice question here for linear transformations in 3 dimensions. So let's just take a look then at this example here for linear transformations in 3 dimensions. So what do we have for this question here? Well, we have this 3 by 3 matrix here, M, right? And for the first part of this question, then part A, it asks us to determine the transformation represented by the matrix M here. So for part A then, how do we do this? Well, the first thing to consider here then is whether the matrix M here represents a reflection or a rotation about the coordinate axes. And I can look at this matrix M here and straight away I can rule out a reflection here, because if this was a reflection, what we get here is either -1, 0, 0 along the first column here, or 0, -1, 0 along the second column, or finally for the third column here, we get 0, 0, -1. Given that we have none of these columns here, right, then it's definitely not a reflection here. So let me just get rid of these just so I don't cause any confusion. So what that tells us then is we have a rotation here. So we have a rotation. So we need 2 things here. We need to know which coordinate axis that we're rotating about, and we also need to know the angle of rotation here. So let's just consider the 3 by 3 identity matrix here. We have 1, 0, 0, 0, 1, 0, and then finally 0, 0, 1 here. Now, why do we consider this 3 by 3 identity matrix here? Well, this helps us to identify then the axis that we're rotating about, right? Because what we're looking for then is which of these 3 columns here does not change then with this matrix M here. Now, straight away, I can see that we're not rotating about the x-axis here, because what we'd expect then, if we are rotating about the x-axis here, is we get 1, 0, 0 then for the first column, which we clearly don't have, right? We have 0, 0, -1. So we know that we're not rotating about the x-axis here. And we know that we're not rotating about the z-axis, right? Because what we'd expect then is 0, 0, 1, whereas we've got 1, 0, 0. So what that tells us then, and as you can see here, they do match up. We've got 0, 1, 0, and we expect then 0, 1, 0. So what that tells us then is we have a rotation about the y-axis here, like so. So in that case then, let's just denote the 3 by 3 rotation matrix here for rotations about the y-axis. So in that case then, what we get here is cos theta, 0, and sine theta along the top row. We then get 0, 1, 0 here. And then finally for the bottom row here, we get minus sine theta. We get 0, and then finally cos theta here. Okay. So this matrix here then, this is the 3 by 3 rotation matrix here about the y-axis. Now, to identify the angle of rotation here then, I need to match up these elements here. So for example, cos theta and 0, sine theta and 1, minus sine theta and -1, and then finally cos theta and 0 here. So in that case then, if we do this, what we get here, as we've just noted them, is we get cos theta, sine theta, minus sine theta, and then finally cos theta here. And that is equal here then to, so we get 0, 1, -1, and 0 here. So 0, 1, -1, and 0, like so. And then from here, hopefully it's pretty much trivial at this point then what the angle of rotation is, but just in case you're still not sure, just consider taking, for example, cos inverse here or sine inverse then. So for example, cos inverse of 0 or sine inverse of 1. And what we find then is the angle of rotation here is 90 degrees. So what we have then is a rotation. We have a rotation here, anti-clockwise. Oh, I can't spell. It helps when you can spell. Try that again. I was never very good at English, so anti-clockwise, 90 degrees about the y-axis. Okay, and there we have it. So that's all we need then for part A. So a rotation anti-clockwise, 90 degrees about the y-axis. Okay, so that gives us the solution there to part A. Now for part B then, let me just box this off here, just so we don't kind of get confused then between part A and part B. So let's do part B over here then. So we're then told that the point A here, which is equal to 2, 3, minus 1, is transformed using the matrix M. It asks us to find the coordinates of the image of A here. So the point A then, let's just denote this here. The point A is equal to 2, 3, minus 1. So to find the coordinates of the image of A here, we need to use matrix multiplication here. So what we do here then is we take the matrix M. So let's just write this down here. So we have 0, 0, 1, 0, 1, 0, and then finally minus 1, 0, 0 here. So this matrix here then is the matrix M. And now we take the matrix here. We take the point A. If we represent that as a matrix here, what we have then is 2, 3, minus 1. And we multiply these matrices together here. So it's up to you. You can do it by hand if you want to. I wouldn't personally recommend it. What I just recommend here is that you just use a calculator. And if you input these matrices correctly then, and we find the product, what we get here then is 1, 3, minus 2 there. Okay. So this matrix here then, what this gives us is the coordinates of the image of A. So in that case then, the coordinates here, so the coordinates of the image of A, so coordinates of A prime, and just in case you've not seen this notation before, A prime just means the image of A here, so the coordinates of A prime, the image of A, they are given as, what do we get then? Well, we get 1, 3, and minus 2 here, so nice and straightforward. So 1, 3, and minus 2 there. Okay. And there we have it. So that gives us the solution to part B, and that gives us the solution to this question here. So that brings us to the end then of this video here on linear transformations in 3 dimensions.